the next thing we're going to study here is impact. And the idea of impact is, your traditional, I've got a, two, like, whatever. What are those things called? Pool balls? Yeah. And it goes bang, and it goes that way. I am awesome, by the way. An impact is basically just having two particles whack each other and studying what they do afterward. And this is great because it's a perfect little application of the conservation of linear momentum, which we've been discussing. So let's get some vocabulary down. And basically, if I got myself, say, two pucks, and one's traveling this way, one's traveling this way. Well, what we want to do is we want to identify the place where they're tangent to each other, right? And this is called the plane of contact. And the plane of contact is where they're tangent to the surfaces. Now, it's really important to get these drawn in correctly, okay? We'll talk more about that why later, but for the moment, take my word for it. All right, so that's the plane of contact. And then perpendicular to it is the line of impact. And that's perpendicular to the plane of contact. So I'll probably end up calling this, LOI, because I'm lazy, and POC, plane of contact, line of impact. Okay? Now, I drew my pictures in like this, or my velocities in like this, but this actually applies no matter how they come in. So if this one's coming in like this, and this one's coming in like this, see, they're not, what's it called? They're not parallel, they're not perpendicular, they're just arbitrary forces coming in any given way. However you want to draw it in is fine, but make sure you know to yourself that those velocities can be anything. But what we want to look at for the plane of contact is tangent to the surface. So even if they draw it funny, so this is a good example. If I draw two coming in like this and one coming in like this, the plane of contact is still going to be tangent to those surfaces. It's the plane of contact. And then the line of impact is going to be, that's not a very straight line, but that's straight. The line of impact is going to be perpendicular to that. Okay, so just make sure that you have those drawn correctly, because we're going to take advantage of that here in a sec. Now, if you draw them coming in like this, or if they, whether you draw them or not, if what they're actually doing is coming in straight at each other, this is called a central impact. And the way that we have them drawn here or here, these are called oblique impacts. Okay, which just means they're coming at a not perfect angle. Okay, good, not too bad. And we'll get more into why we need to know all this later. I'll assume, but anyway. The first one we want to look at is, let's just study a central impact. Now, this applies in general, but it's just easier to understand if we look at this simple example. Okay, so let's start with our little particle. And he's like, yay! And here's the other particle. They're happy. So we have A and B. And A is traveling with velocity VA1, and B is traveling velocity VB2. And we're assuming that VA1 is greater than VB2, so we can say, so they're going to crash. Right? Does that make sense? A is going to catch up because it's traveling fast. So they're traveling along, and then finally they bump into each other. And, they smush into each other. Okay. Now, and this is the title, because this is really important. Central impact. Now, what we're going to assume is that they are deformable. Because, if we didn't, then it'd be boring, right? So, now that they're deformable, what's going to happen is that they're going to smush, okay? So B exerts a force on A. Let me draw it a little bit better. B exerts a deformable force on A, and A exerts a deformable force on B. And the way we're going to represent that is integral P dt. And so our deformation force is given by P. So we're going to sum up all our deformation forces as time passes. But we are deforming each other, we're smushing each other, and these are equal and opposite. So we've got a negative P dt and P dt. Okay, and they're still going at different velocities, but they're still making progress. All right. I feel smushed. Okay. So they're going along, making all kinds of progress. So now, at the maximum time of deformation, would you believe that they're both going the same velocity? Does that make sense? Because it's like you're throwing them, and then they stick together, and for that instant that they stick together before they bounce back apart, they're going the same velocity, because it's like they're one particle. Does that make sense? This is really important. This is like when they smush together, they're like one particle at max deformation, going at some straight velocity. So this is at maximum deformation. They're going the same speed. Got it? And then finally, as they continue to make progress, now that once they are maximally deformed, now they're going to start pushing back on each other. So he's going to say, no, no, get away. And he's going to say, no, no, you get away. And these are called our restitution forces. And they are also equal and opposite. Okay, so now they are coming back apart. So this is like your smushing force, and this is your bouncing back or your unsmushing force. I don't really know how to spell smush. Unsmushing force, and then after that happens, then they are finally separate in their perfect shapes initially, and the B2 is going with velocity A2, and we assume that now VA2 is smaller than VB2. That, now that they hit, they're not going to hit again. VB is going faster than VA. Okay. So, in general, in theory, we assume, that the restitution forces are equivalent to the deformation forces, or that, really how I should write it is that these, when you add them together, you're going to end up with zero. That you're going to have a net nothing difference. That they're all going to turn out to be great, and that it fully bounces back. But if you have any experience smushing things, you're aware that usually when you smush something, that it never unsmushes perfectly. You got a Coke can, and you smush it. That's a bottle, but if you smush it, it's going to go, and then when you try to unsmush it, it's going to come back, but it's not going to be perfect. There's always going to be that one little bump that you can't get out. And that's kind of the same thing. So that's kind of the way you want to think about it. Because in reality, we always push harder than we can recover. So this is our recovery, and this is our smush. Our smush is always greater than our recovery, so maybe it will look better or make more sense to you if you write it, PDT, PDT, is greater than our dt. So our recovery is always, our recovery over here is never going to be as good as our smush, right? Because, you know, I mean, that wouldn't make any sense. I mean, in real life, you could never recover more. So, I mean, if you want to say theoretically, it could be less than or equal to, but R is never going to be greater than P. That wouldn't make sense. You could never, you know, you would never see a ball that you hit it and then it becomes a bigger ball afterward, you know, a bouncier ball. I mean, it's always going to get worse. So keep that in mind, and we're going to use that here in a sec.